video on L matching networks, I explained that if you recall, if you have unequal source and load impedance, well, what you can do is you can design a two-element L matching network in an inverted L fashion. For example, over here, if you recall, what we did was to place the shunt reactive element, the shunt reactive element. This is the shunt reactive element with the higher impedance or higher resistance, which in this case is the source resistance, and the series reactive element with the low impedance, which is the load part in this case. Okay, so we have an inverted L section over here in this case, and this is your two-element L matching network placed between this source and load. Now, what we did earlier was to consider the impedance seen looking towards the left, and it turned out that this had, if you calculate the parallel combination of RS with shunt reactive element GXP, it turns out that it has a real part R left, and then it has a imaginary part JXL, let's say. And the idea was to match the real part with the real part of the right hand side of the circuit, and the reactive part is the negative of the series reactor. Okay, because it has to cancel the effect of, because once you're putting up a shunt reactive element which is not the part of the original circuit in parallel with the source resistor, okay, then you will have both real and imaginary parts. Okay, so the imaginary part is to be cancelled with the negative of minus xs. Okay, so x left is to be set equal to minus x of s, or x of s is minus xl, same thing. So you cancel this part. Okay, so you are putting a series reactive element just to cancel the imaginary part of z left, which is xl, and the real part is set equal to 10 ohms. Okay, from that you calculate the variable of xp. Okay, and similarly your xl is minus xs. So you have these two reactive elements. Whether they could, if you're going to select xl as an inductive reactance, then xl is j omega l. If it is a capacitive reactant, then this is 1 over j omega c. Okay, so this xp could be your 1 over j omega c or j omega l, whatever, however you're going to select it. Okay, well, it's a reactive, it's a capacitive element or it's an inductive element. But it turns out, if you remember this procedure, it's a little bit more time taking and involves more algebra. So a better idea is to consider the quality of the circuit in terms of the impedances, the load and the source resistance in these cases. So if you consider the quality factor of the circuit, which is given as square root of R high over R low, in this case R high, for example, is 1000 and R low is 10. So if you're going to calculate the quality factor, okay, it turns out to be about 10, which is much greater than 1. So we are talking of a very high Q circuit. So you see, the point is, when the Q is large, the two elements in a two-element reactive L matching network, you have nearly equal and opposite reactances. Okay, so this is what you're getting: X parallel and X series. Over here, this is X parallel. Okay, and this is your X series. They are nearly equal and opposite. Isn't that right? You see, for a very high Q circuit means you're going to have a very narrow band match, and the bandwidth is small. The 3 dB bandwidth is small. The peak is large, so the matching could be something like this at the design frequency. Okay, if this scale is versus frequency, this is a high Q matching. This is the amplitude or the power transfer. Okay, so that's your the design frequency at which the maximum power is desired to be transferred. So it turns out that if your source and load impedance are different, much different, the difference is high. So that means this ratio is high, okay, and then your quality factor turns out to be a high Q, so you have a narrow band match at the desired or the design frequency. And then this Q can be shown for example, for the parallel shunt reactive resonant circuit, and for the series resonant circuit, this can be written as R high over X parallel, and this can be shown as equal to X series or R low. For example, for a series, if you recall, for a series RLC circuit, you have J omega L over R. That's your Q, the quality factor of the circuit. Okay, for a series RLC circuit. So that's your reactive part over here. So it's again, it's the quality factor of the circuit, and it can be written for the parallel as R high over X parallel. Okay, so it's just the reciprocal of the parallel resonant circuit, the reciprocal of the quality factor is the reciprocal of the series resonance, series quality factor. Then using these two expressions, you can evaluate X parallel, the shunt part, and the series reactive part, X series. So for example, over here in this case, you have RSS 1000. The 1000 over X parallel is your 9.95. That's the Q that is set from the source and load impedance. Okay, that is set. So you can find X parallel as 100.5 and series as minus 99.5. For the reason for minus is that you are selecting a capacitive. This is capacitive. This is capacitive reactance. Okay, so that's why you have a minus sign over. So these are nearly equal and opposite. If X parallel is inductive, then it comes with a positive sign. Okay, but then again, it's not necessary. I mean, this could be, for example, this parallel could be capacitive, and this could be inductive, and then you will have a negative sign over here for capacitive, positive sign over here for inductive series reactance. But then they are nearly equal and opposite at which they are going to resonate. So if you consider this schematic in ADC, in ADS, this is a linear circuit analysis. If you're going to run an AC analysis for this circuit, you have 1000 ohm over here, which is the source resistance, and then you have a load resistance of 10 ohms. Okay, I think we have considered this before in the part 1 series of this matching network. It turns out that this inductance is 10.66 microhenries. Okay, so this is your inductance, and you have a capacitance of 1.07 nanofarads, which is over here. This is your series part. Okay, I mean this is calculated as such. This is 1 over omega c. Omega is 2 pi into your design frequency f c, and this is your simply 2 pi FL, which is your inductive reactance, and F was set to be is set to be equal to 1.5 megahertz. Okay, which was the it is said to be in the range of AM broadcast, near the top end of the AM broadcast range. So for 1.5 megahertz design frequency, you find out these values, set this to 1.5 and find C and L, and you get this 10.66 micro and 1.066 nano, and then you run the AC simulation. So these are the values. This is my shunt reactance. This is my series reactor. Okay, and this is how we are going to match 1000 to 10, and that's my magnitude of the power that is transferred with respect to the frequency. You can see the maximum power occurs at your design frequency, 1.5 megahertz. So when the ratio of the source resistance to the load resistance is much different from unity, so it means your Q is high. The L network produces a very narrow band match. It's a pretty narrow band match, which is very desirable. The match is good, but it is only very close to the design frequency. Okay, you see at near DC, what happens at DC is that this capacitor is open circuited. Okay, so you have an open circuit over here, which we talked before as well, and then you have a short circuit here. The inductor is shorted out at DC, so there's no power that's being transferred. So there is no power being transferred. But at high frequency, you have a mismatch. So there is a mismatch of load and source impedance. Actually, at high frequency, this circuit pretty much reduces to itself. It's just like your you have source resistor of 1000 ohm with let's say an ideal voltage generator at high frequency. and then you just have your load part, okay, which was in this case equal to 10 ohms. Okay, so you have actually 1000 RS, and you have 10 ohms of this is the load resistance, and then you have the source, ideal voltage source. So what happens at high frequency is that this becomes an open circuit, and this becomes a short circuit. Okay, this is open, nothing is over here. Okay, so it's just like you are connected 1000 ohm source resistance to the load resistance. Okay, this is a short circuit. So this is what is happening over. So due to this mismatch, you see the power transfer is very small over here. We're not transferring much power to the load side. Okay, but maximum occurs at 1.5. Well, that's one way to look at the design. Okay, so quick ways to just to if you can remember this formulation for the quality factor of this circuit, then in terms of R high and R low, okay, you can calculate the quality factor. Okay, then from the quality factor, you can understand if it is a high Q, you will have a very narrow band match. As you can see over here, it's a very high Q match. It's a high Q match, which means the 3 dB bandwidth is small. Okay, it's a high Q match, which is very desirable. So then you can quickly find from the source resistance and the load resistance, high or low, whatever it is, you can find a parallel and series reactive elements, and then it's your choice whether you are going to set it to be an inductive reactance or capacitive reactance. Okay, there's a negative which shows that capacitive reactance. So you find this, you from there you find the circuit elements, okay, and simulate the response, simulate the frequency response, and this is what you're after, what you so much desire, and you have a perfect match at the design frequency. The maximum power is being transferred. Now, what happens if in this case we have a very high Q matching? What happens if we increase the load resistance? Okay, what happens if we are going to increase the load resistance? Well, from here, 10, if you're going to increase it 10 fold, you make it 100, then that means 1000 over 100 over here is going to produce 10 minus 9, so Q is 3. So the Q is low. Low Q means wide bandwidth match. So let's see over here what happens. So what's going on over here is you have increased the load resistance 10 times. So what we are going to expect is when the impedance ratio is close to unity, the match is wider. Okay, so over here the Q has dropped to 3, and then from the same formulations you can evaluate the parallel and the series reactances, and those are a little bit different as compared to what we had earlier. These reactances were very close to each other. These are close because 1000 and 10 are very much different. Those numbers are different. Okay, the ratio is high, 1000 to 10. But over here, these numbers are, the ratio is 10. Okay, the ratio is dropped. Q is dropped. Okay, so there's, you see the difference over here. And then from these, if you're going to set this the parallel reactive element as an inductor and the series element as a capacitor, these are the element values which you can obtain. And then if you calculate the P out, which is V out square over 100, this time is the load is 100 for the same source resistor 1000, and you run the AC analysis, linear AC analysis of the circuit from 0 to 5 megahertz, and this is what you get. Okay, so this blue curve, this thick blue curve is for my RL equal to 100. This was 100 ohms. Okay, RS is the same. RS, we are just considering the effect of increasing the load resistance on the bandwidth of the match. So my RS is set to 1000 ohms for all the time, and I'm just increasing my load resistance, and this bottom curve is for RL equal to 10 ohms. Okay, and if you recall, the quality for this red curve at the match was about equal to 9.95, or about 10. Okay, so the quality of the above curve has dropped to 3, the quality of match. So you see a very wide band match. And again, at DC, you see this, the behavior of the circuit is pretty much the same. At DC, the capacitor opens up, inductor is short, so there is no power that is being transferred. And then at the high frequency, there is a mismatch. So this is your mismatch region. and at mismatch you are compromising your power, okay, compromising the power uh, which is being transferred to the load, okay, due to uh, the topology of the circuit. You're just connecting the source resistor to the load resistor, and since there's a mismatch, but again, you see this mismatch has decreased. So owing to the decrease of this mismatch, you have more power as the blue curve shows more power transfer for 100 ohm load as compared to 10 ohm load. Okay, those are the points to be considered. 10 ohm is further from 1000, so mismatch is more, right? Now, again, if you're going to increase this 50 times 500, the load resistor RL still increased to 500. Well, this ratio becomes small, okay, and the quality factor reduces. This Q becomes equal to 1, and then from this Q you find out your X parallel and X series. Again, there's a lot of difference between these two numbers, okay, and from these two numbers add the design frequency of 1.5 megahertz, 1.5 same design frequency, 1.5 megahertz. You can evaluate your reactive. So X parallel is your inductive inductive reactance, and this is your 1 over omega c, so it comes with a negative sign. You can evaluate the inductance and capacitance values, and this is what you get over here in the circuit. Okay, so this is your again the power P out which is being delivered to the load, and you see at the design frequency, again you have the maximum that is being transferred to the load at this point, but in this region, okay, all three curves they agree that the maximum power is transferred. At DC, you have no power transferred in all three cases. But as your load resistance is being increased, this is 500 ohms. So this is, since the load resistance is increasing, the power is increasing. This is at 100 ohms, okay. In all three cases, well, there is mismatch, but the mismatch is also reducing, okay. The mismatch is also reducing if you're going, you're looking at the above curves, the blue one and the pink one, okay. So this is 10 ohms. The Q for this is 3, sorry, it's about 10. The blue curve, we have Q equal to 3, and for the pink curve, we have Q equal to 1. So that's why you see have a very wide band match, because 1000 and 500 are close to each other, okay. So you're going to have a very wide band match, but as the load resistance is different from the source resistance, which is for all the time set to 1000 ohms, for a high mismatch like in the red case, you have your power is dropping. So this region is again your mismatch region. This is your mismatch region. Okay, but again, if you are going to increase this the load resistance, well, you're coming close to the source resistance. Okay, at the expense of a very wide band match. So that's all. But if your load resistance is small, the Q is high, and in that case, this topology is the way this LC are connected. You have a very high Q match at the design frequency.